So differential calculus then, introduction to differential calculus. It's the mathematics of change. We use it to find the rate of change of something. And there's notation that we use to represent this rate of change. So if I've got a function and I plot a graph, y against x, and I get some sort of curve, this represents the change of y with x. As x changes, what happens to y? This is often time, but it doesn't have to be. So how is y, the variable on the y-axis, which could be force, could be voltage, could be current, how is that changing with time or some other variable? Okay? And this graph shows that function. So the rate of change of y with respect to x is what we get when we differentiate something. So dy by dx is the differential. Function. Dy by dx is how we say it. And it tells us the rate of change of y with respect to x. With respect to, often abbreviated to WRT, with respect to x. So when we learn the rules of calculus, what we're doing is we're finding a new function called the differential function, which tells us the rate of change of y with respect to x. And the rules are not that complicated to learn. And once you've got them, as I was saying before, then you can quickly do it. You can quickly find how y changes with x. Find this new function. With respect to. Another way of representing the differential function, another notation, another notation. If I have a function, f of function, with respect to time, or how, so this is a shorthand way of saying some sort of function where t is the variable, t is the independent variable, the thing that's changing, time. And if I want to find a differential function, then the notation, instead of writing dy by dx, is to write f prime t. So this is the differential function as above. The differential function. So, well, there's two ways we can write the differential function. One is if y varies with x, and we've got some sort of expression or equation that relates y to x, dy by dx would be the notation I'd use to represent it. If I use this sort of notation to represent the function, ft, where t tells me the independent variable, then f prime. So it's the prime here that tells me this is the differential. So just one more example of that. That could be a different function. F is not always used for function. In fact, that's probably a bad example because f, you tend to think means function. I could just as easily use the letter g to represent a function. So another example might be gx. So that's a more general one. g is the function, x is the independent variable. So if I want to represent the differential of that function, g prime x would be the differential. So that's the notation. And we use differential calculus to find the rate of change of a function of one variable with respect to another. So this first one is probably the more, tells us pictorially more what's going on. If we look at this graph, that's telling us how y varies with x. The differential of that function, dy by dx, tells us the rate of change of that function of y with respect to x. If we look at this curve, the gradient is actually the rate of change of y with respect to x. So in fact, the differential tells us the gradient of the curve. So at this point, the gradient would be in that sense. At this point, we'd have a negative gradient, a bit steeper. At this point, and this is an interesting point, we've got 0 gradient, and that's interesting because it gives us a minimum value in this case of the function. So the differential tells us the gradient at a given point, and that's a particularly interesting one that we'll come on to. So the differential of a function gives the gradient at a point. And that's important, at a point. So back to this graph again. The gradient at a point is given by the differential, the gradient at a point. If I wanted to find the gradient of a curve, I'd have to draw a line which is a tangent to the curve, and then put a triangle on it and find the gradient that way. Gradient, remember, is y divided by x, so y over x would give me the gradient. What calculus does is asks the question, what happens as this triangle gets smaller and smaller and smaller and approaches the gradient at a point? And the rules that we're going to write down come from just exploring what happens as the triangle gets smaller and smaller. And differential calculus from first principles is in the textbook. So if you want to look at how we differentiate from first principles, how these rules that we're going to write down are arrived at, you can look at it. And it's all based around this idea of asking what happens as the gradient, or as these 2 points, as this triangle gets smaller and smaller and smaller. And we get this delta y, the small change in y, over delta x, the small change in x. So that's what that's about. But we're not going to go into these first principles. We're just going to write down the rules. Okay? But these rules, once we've got them, will tell us the rate of change of y with respect to x, which is the gradient of the curve at a point.